Welcome to this course titled Modeling Stochastic and Turbulent Transport. Now, this rather unyieldy title is a consequence of me wanting to include certain keywords. So, one is stochastic, and we are going to be looking at situations of mainly mass transport where the underlying processes that give rise to mixing, spreading and transport are stochastic or apparently random. So that's where stochasticity is coming. The obvious situation is thermal noise driving things like Brownian motion or diffusion. And I also wanted to throw in modeling, because that is the main point. Right? So as we will see in a kind of soft way, I will introduce the basic idea in this lecture. So that's why we have these three aspects, and the modeling part is important. So even though I will be focusing mainly on mass transport, you can use these ideas of how to treat stochastic systems and the associated math to whatever stochastic problem that you may be working on in your projects. Okay, so let's begin with the turbulent part. So here you have a picture from the Journal of Fluid Mechanics, which is a simulation of a flue stack. So you can think of some kind of power plant, which has a high tower that's emitting some hot gases. And what you see here are temperature contours of the gas that is being emitted. So on top, you have an instantaneous snapshot of the turbulent flow of these gases. And in this snapshot, it's very clear that you have these complex eddying structures, with fractal-like surfaces. And of course, as it is spreading downstream, so you can imagine wind is coming right from my right towards my left, and that's dragging the noxious gases away. But you can see that the turbulence is creating quite a chaotic kind of situation at any instant of time. Obviously, in some sense, things are spreading, right? But it's complicated. Now, what you see below is what you would get if you observe this phenomena for a long time and then average. And because, as we'll understand what it means later, but because this turbulent situation is statistically stationary in time, it means the statistics don't change in time. So looking at a long time, making a movie for a long time and then making an average instant single picture is the same as looking at several thousand of such stacks at any instant of time and averaging them. So the ensemble average is the time average in the stationary process. Anyway, so the bottom is like in some sense a mean of what is happening. And you see that that is very nice and ordered. You can see that there is a kind of spreading in the mean sense, right, as you go downstream. In fact, if you model it, it will be close to something Gaussian, right, like a bell curve, which comes out of diffusion. So this is the, if you like, at an instant, the idea of eddy diffusion. So I guess some of you all would have seen and heard of eddy diffusion modeling, right, of turbulence. So this is kind of a physical picture of this. Now, this actually also brings to the fore the delicious irony of turbulence, right? Which is what? So we can describe the instantaneous snapshot exactly with the Navier-Stokes equations, right? Augmented with thermal equations, etc. So that is the top. So our computer simulations, what we know, our maths, our physics, right, can give us the top picture. But that is extremely complicated. It's chaotic, right? It's hard to know what exactly to ask about this, right? So if you have such a complicated situation, what can I say about it? It's anyway complicated. At every instant, it is fluctuating. If I repeat the experiment, I will see a different time history, right? So that the stuff that we can predict from the governing equations is very complicated and hard to get a handle on. Now, the average behavior below is nice and ordered and relatively simple, right? The picture in the bottom panel. But I don't have the equations for that, right? I have equations for the instantaneous behavior, not for the time average behavior. And if I try to get it from the Navier-Stokes, I cannot do this. It stays an open problem, right? Again, if you have looked at Reynolds averaging in some previous course, you will know that higher order moments stay unclosed, and then you need some kind of approximation model, right? Eddy diffusion is one such thing. Anyway, so this is the point, right? And this also highlights the fact that the challenging problems like turbulence lie in between fully ordered and fully random systems. Another way to say this is, suppose that complicated eddying motion had an effect that was purely random. It was like having random swirls doing random things. then I could just model them in some random way and get the picture below. But this is not true, right? Because those eddies on top have to satisfy momentum conservation, energy conservation. They can't do anything random. So even though it looks chaotic and random in some general way to us, right? Obviously it is not. It's governed by Navier-Stokes. So that brings us to Henri Poincaré, who made an interesting point in his book Science and Method, published in 1908 in French. And there are English translations, of course, available. It's a nice small book. You should think of getting it. Anyway, so what he said is the following, that very simple systems, like take planetary motion, for example, right, where there are few variables and the motion is ordered and cyclic and periodic. These are easy to describe, right? And that's what we did starting from Newton and for 16th, 17th centuries. So those are, in fact, the first systems that physics and mathematics could conquer, right? Very simple, few variables, ordered motion. Think of simple pendulums, right? Balls rolling down inclined planes and so on. So those systems are easy. Right? Then later on, the other set of systems we were able to solve were on the other extreme of huge number of degrees of freedom and completely chaotic, right? So you think of ideal gas, right? Where you have a huge number of molecules, or if you like billiard balls, right, bouncing around, doing completely chaotic things. But we can predict their mean behavior because of randomness, law of large numbers. Effectively, you can use probability theory to get simple answers, right, which work very well. So in other words, we can treat a single ball or a simple pendulum or planets, right, a few planets, and we can treat a huge number of molecules doing things that effectively become completely random in an ideal gas. The problem lies in the middle. Okay, and this is what he identified way back, and 100 years later, those are the kinds of problems that we are still struggling with. And in fact, those are the kinds of problems that we are most interested in. So just one example is you take any biological system. This is the human lungs. Right? For something to be alive, it cannot be completely random, right? Then that's what will happen if you take any system and crank up the temperature, right? Things will become completely random, but such systems are usually dead. So if anything is alive and interesting, it has a combination of some order, but not completely ordered. Otherwise, again, you will just be doing nothing, you'll be dead. So in between is where things are interesting. So you think of the lungs, right? The lungs are lined with cilia that transport mucus, okay? And this is a complex system because it is multi-scale. You have small, tiny cilia, but these are spanning the entire lung airway, right? At the same time, the mucus is a complex fluid. It's not like water or honey. Right? It has its own internal polymer molecules and whatnot. Right? So you have to contend for information at different scales, and some things are happening apparently randomly. So there will be molecular fluctuations that affect how the cilia beat, that affect how these polymer molecules behave. But at larger scales, there will also be some order, right? Because in the end, the mucus is being driven out of your lungs. But you have to describe things across both scales. So one example is this. So many biological systems have to contend with this combination of order and chaos. So that's a detailed picture of what I was saying. And another nice example which brings the turbulence aspect in is cloud streets. Okay, so the image that you see here is so this is the land mass, okay, which is ice-bound and cold. And then you have the ocean, which is comparatively warm. So you usually get, and these streaks you see are really bands of clouds, okay, which are very beautifully ordered. And this usually happens when air flows from the land over the sea. Okay, so then it brings cold air from the land on top of the sea. So you have warm sea and then you have cold air on top. Right? So then the stuff below is hotter, less dense, and tends to convect. Okay? But the spontaneous convection you get self-organizes, right? And you get these beautiful bands of clouds. This is another picture, right, where you also see this kind of ordering. So this is another example, right? You have clearly the clouds inside, it's going to be turbulent. Right? So on some small scales, things are completely turbulent. But on very large scales, you see that there is this very nice order. And the challenge is to predict that large scale order when you have all this small scale turbulence. Right? Not very dissimilar to the biological system, where at small scales inside the mucus you have polymer molecules undergoing random fluctuations, but giving you large scale properties which seem to be ordered and reproducible. Okay, and that's what brings us to the math part of this course, right? So when you want to deal with these two things, order and chaos together, that's when you get stochastic differential equations quite often, right? So again, you think about the examples I've given you. You think about the simple pendulum. Obviously, you write Newton's laws for that, you get a differential equation, ordinary differential equation, which you can solve, right? You know how to solve this problem. If you can't solve it analytically, you can easily do it on a computer. Then on the other hand, you take a fully complex system like kinetic gas, right? Then you can use probability theory. You can also do simulations using purely random numbers, right? And you can do stuff. Right? Now, in between, you have to combine both. So think about this cloud system. Suppose I want to model the small scale turbulent fluctuations with some randomness. I can do that, but I also have to account for the large scale organization of the pattern, right? Which will require some kind of differential equations. So it's this combination that will give us stochastic differential equations. Okay, so now I've been talking about stochasticity and randomness in the context of transport. So let's look at two examples, okay, which show you the two typical cases we'll be dealing with. So one is Brownian motion, okay, and diffusion. So I guess you're aware of this basic idea, right? That if you have a slightly larger particle in a bath of smaller molecules, right, the large particle will be bombarded by the small molecules randomly. So you can imagine this yellow particle, which is the slightly bigger, heavier particle, gets bombarded all the time. And because there are so many molecules hitting it, it's like a random force. So the molecules will sum up, the impacts will sum up and give you some net force. But that net force will fluctuate in some apparently random way. Okay? So because of that thing, this thing will do a random walk. Okay, and that's what we call Brownian motion. And what will lead, if you have many of these yellow particles, that will create diffusion, right? Because these particles will spread out slowly. So we are of course familiar with this idea in standard courses on mass transfer. And if I look at just one, I can see it do this kind of random walk. If I take an ensemble of them, right, which means so you can think of taking many at one time, and if it's very dilute, this will work. But to be very precise, what you want to do is an ensemble. Right? You take only one, you watch what it does, you repeat this experiment 1,000 times, and then you see what is happening to the population. So that will give you statistics. But if you have a dilute enough system, you can do many at the same time, which means sufficiently dilute, they won't see each other. So their motion will not be affected by colliding with their neighbor. Right? They're doing their independent stuff. So that's what I mean by very dilute. So if you look at an ensemble of them, you will see something like this, right? If you look in three-dimensional space, it will spread out like a cloud, the population. Right? And then if you look at any projection, you will see it spreading out, right? So it's like, and in fact, you can maybe roughly tell that it will have some kind of bell curve distribution, if you think of the probability distribution of being at some place at some time. Okay? So this thing will keep spreading. So this is just to set the basic idea of what we mean when we talk about Brownian motion of individual particles. So the question was, I was talking about a situation where we have one large particle in a bath of small things. What happens if you reverse it? So I cannot give a general answer to this. It really depends on the specific setting. But one way to think about it is you think of a particle moving in porous media. Right? So the porous media is like big particles in the limit where they are so big they don't move. And you have a tiny particle trying to migrate around. The question is, why is that small particle going to move? So it's an odd sort of setting. But if I imagine that the small particle is anyway diffusing, then the big particles act like obstructions. Right? Or another situation, you think of a pinball machine, which is maybe more like what you're asking. Right? So you think of a pinball machine, that is this. Right? You start with a small particle, you give it some initial velocity. If there is no other thing, it will just go in a straight line. If there are other big stuff around it, those are like obstacles. So it bounces around, and it will end up doing something chaotic. Yes, so again, we can maybe discuss this later, but it's possible that a small particle will, it has to have a reason to diffuse. So that small particle has to be in a bath of even smaller things, otherwise it will not diffuse, it will just sit. Diffusion happens because of the fluid bath. If you just take molecules in vacuum and you leave it, it will just sit there. unless you give it initial velocity. So anyway, we'll discuss this later. But in this, the whole point here about small and big is because it is massive compared to the small guys, their bombardments can be treated randomly because you are adding the forces of a large number of molecules. That's why it becomes random. If you just have 2 particles, what you will get will not be random. Okay, so let's move on now. This is the usual diffusion situation. Now we look at a situation of similar kind of diffusion, but that happens because of turbulent flow. Okay, so the specific setting is what is called bacterial turbulence. That's not very important right now. We'll return to it till later lecture. But the idea is if you take bacteria in a petri dish and you give them enough food, okay, then they start swimming. Bacteria swim, right? So if you give them enough food, they start swimming fast. And if you concentrate them enough, then the suspension starts to develop turbulent motion because of the bacteria swim. Right? So the bacteria swimming, it pulls some fluid along with it. And if many of them are swimming, the entire petri dish will start, you'll observe a turbulent kind of motion arising out of it. So this is called active turbulence or bacterial turbulence. What's interesting is you have a turbulent-like state even though the Reynolds number is extremely small because you'll have a very thin layer of liquid in a petri dish. Okay. So anyway, that is not important. What's important is that there is a flow, okay, that is apparently random and chaotic. In that sense, it is turbulent. And now if you put dye inside this, you will see that the dye mixes. Okay. Or if you put a tracer particle, that tracer particle will mix because of the motion created by the bacteria. So it's a flow-driven transport as opposed to the first earlier slide where it was transport by molecular motions, thermal motions. Okay, so that is the distinction I want to make. So what you are seeing here is a simulation of this kind of bacterial turbulence. So you have a simulation that produces the flow field, and on the images on top, these are the vorticity fields. So the flow field has got very small vortices like eddies, and they are rotating and moving around in some complex way. And what's interesting now is if I put a dye into that fluid, the dye will start to spread because the flow field is complicated. Okay. So this is what we mean by turbulent mixing. It really is turbulent mixing, just in a different setting. And what I want you to notice is in the movies below, which will show you how an initial dye placed is going to spread. And there's some color scheme to show you the dye on top is color different from the dye below. Okay. And notice a similarity to what you saw before. So there are 3 movies because there are 3 different intensities of the bacterial turbulence. As you go from my right to my left, the intensity increases. So this extreme case does something more strange, okay? But especially if you look at the level of intermediate bacterial turbulence, you see it looks very much like diffusive mixing. So let me play it again for you. So if you were to just look at that movie, right, this one, and you don't know what is the source of this mixing, you might as well think it is some kind of diffusive random box. Right? So the point I want to drive home here is if you just think about the outcome of a turbulent flow in terms of transport, it has some similarities to thermal driven diffusion. Right? And that is a typical idea we have. Right? We know that if we induce turbulence, we'll mix things. Right? That's why you stir your cup of tea when you add sugar, etc. Right? So you are creating turbulence to mix. Right? And you can do this at the large scales because if there's enough inertia in the fluid, it will spontaneously become turbulent. But suppose you have honey, then you cannot do this. Right? You cannot mix something in honey by making it, it will not become turbulent. However, that's why I wanted to show you this example. Right? So this is something like a very low Reynolds number setting, but by using bacteria, you can create turbulence. Right? So there are all these interesting things. But the point I want to make is that you can see the similarity now if you just look at the transport. And that's what this course is going to be about. Right? We're not going to worry so much about the Navier-Stokes equations and how turbulence is arising. Right? That's fluid mechanics that we have studied, and of course there are many questions there. But what we're going to look at is the outcome, right, for transport. So we are going to take the motion or the field as a given, right? So I start with a velocity field that is turbulent, it's coming somehow, fine. And now I put a dye inside, and I can see that mixing is happening. How can I describe this mixing? Can I describe this mixing by using some kind of diffusion-like model? Then that is basically eddy diffusion. Or is there some issues with doing that? Right? Is there some signature of the fact that the flow is governed by the Navier-Stokes, or does it not matter? Right? Can I completely replace? If I could do that, then I can, it's basically saying throw away the turbulence, just treat it as a random fluctuating field. Right? And that's an important thing. That's a big simplification. But as you will see, it's not, I mean, obviously we cannot do this, right? Otherwise we would be able to solve all turbulence mixing problems. And the question is why? Okay, so this is one example of why things are not so simple. So what is done here in this PRL is they have now put an individual particle and allowed it to move with the fluid and tracked its mean square displacement in time. Okay, so again, something you may know from simple diffusion is if I observe one particle and it's doing this random walk, okay, Brownian motion, and if I look at the distance it covers from its initial starting point, I call that delta x. So with time, of course, the delta x square will grow, right? So I have to do many experiments, ensemble average, look at the variance of delta x square, and that will grow in time, right? That's what's plotted here. And usually it grows in time linearly. So delta x square will grow like t, okay? Or the standard deviation delta x goes like root t. So that root t behavior is a classic behavior of diffusion. We will derive this later in the course. Okay? So now what is seen here in the turbulent flow, you can do the same exercise. You can put a particle, it is not undergoing Brownian motion, it is being advected by the field. But because the velocity field is chaotic, it also will go back up and down and so on. And I can do the same mean square displacement thing. And what you find is that at short times, delta x goes like t. That means delta x square will go like t square. That's what you see here. Right? So what does that mean? If I am sitting with a fluid and I move with the fluid, delta x will be equal to the velocity times delta t. That means delta x should go like delta t. So that's what the t square is showing you. That tells you that, oh look, there is a flow field, it's moving with the velocity of the fluid. Right? So this is not diffusive. It doesn't look like diffusion. But at very long times, so this is the time axis, right? So it means if I put the particle, I go have a cup of tea and I come back and now look at the particle, right? I'm looking at it over long time scales. And if I do that, in that time interval, there are so many chaotic eddies that the outcome starts looking more like random walks. So you see at long times, the behavior becomes like diffusion, right? So delta x square goes like t. So this is the important point to keep in mind, right? So this already shows you that if I were to look at it very carefully at very short times, it will be obvious to me that there is a flow because it will be moving ballistically, right? It's moving with a velocity. But at long time scales, it will look like it's taking random jumps. And that's what you can see here in this mean square displacement. Now what's interesting is if you do this for different levels of the bacterial turbulence, right? Remember you saw in the movie some strange things start to happen, it starts to move in a crazier kind of ways, right? Not so diffusive. That also shows up here. So if you go from the bottom curve to the top curve, the turbulence intensity is increasing. And you see that for milder turbulence, you get diffusive-like behavior. So that is what you saw visually, right? It's spreading like a diffusive cloud in the middle video. But if at the highest levels of turbulence, which is what you saw in the rightmost video, you get a super diffusion. So instead of delta x square growing like t, you grow like t to the 4 by 3, which is a stronger power. So you are spreading faster. And that's in fact very obvious here. So now I want you to compare these two movies, right? This is the one that shows you diffusive like spreading. This is the one that is super diffusion. So of course, super diffusion, it's not an oxymoron because we're not talking about diffusion in terms of thermal motion, right? It's some other phenomena giving you a behavior that looks at the first sight like diffusion, but actually is not. Right? And it spreads faster, and you can see, right? There are like these jets. Specifically, they're called levy walks, but you know, there are big jumps basically. And these jumps are much larger and much more frequent than you would expect for a thermal process. So just visually, you can tell something very different is going on, right? This is spreading much faster. And that shows up in the statistics. So again, coming back to our course, right? If we want to model these things, right, that was the third keyword, right? How do I model such phenomena? If it was just doing diffusive-like things, I would say, fine, it is effectively, no matter what the turbulence is doing, my particle is moving like it's doing a random walk. So I'll use the usual mathematics of Brownian motion. The only question then is, how should I set the effective diffusion? Right? So if some sort of diffusion behavior is happening, in case of actual Brownian motion, I'll use Einstein diffusivity, for which I have a formula. Given the temperature, given the mass of the particle, etc., I can calculate the diffusivity. But how do I calculate the diffusivity in this case? Right? Obviously, how much it is spreading depends on how turbulent the flow is. Right? But what is the relationship? But things are even more interesting here, in the third case, which is superdiffusion. Because now I cannot use the usual mathematics of Brownian motion. Right? I cannot just, the question is not only what is the effective diffusion, because it's not just diffusing. Something else is happening. And how is that something else, that superdiffusion, related to the dynamics of the problem, to the fluid dynamics? So these are some of the modeling questions that one would address if you have before you some phenomena that looks random, that looks diffusive like, but you know from what the experiment is that it is not just thermal motion. But that's the kind of system I really want to describe. Right? That is the same here in this third panel. Right? And that is the same question here. You see? So I have something. At first glance, the bottom panel looks like there is something that's just diffusively spreading. Right? But you know that it's not really coming from thermal motion, it's coming because of turbulence. In the other case, inertial turbulence here. The other case, it is bacterial turbulence, and you can come up with other examples of problems where you need not have anything to do with turbulence, but there is some other mechanism giving you random like spreading and mixing or whatever. And the question is how to describe such systems. Right? So you need something more than the usual Brownian motion, Brownian dynamics stuff, and that's what we'll do in this course. Okay? But to be able to reach there, we need to start with the basic stuff. So we're going to start with Brownian motion, right, and learn the basics there, and then see how we can extend it. Okay, so are there any questions at this point? Yes. Yes, so the question is what is the cause of superdiffusion in this particular problem? So indeed it is the fact that when the turbulence becomes more intense, the character of the flow changes. So whereas in the milder flows you have nice vortices swirling around chaotically, the vortices are almost like, if you like, gas, bubbles of gas moving around or something, right? So in the other case, the flow changes and you get jets. So it's in between these vortices, there are these big jets that burst through somehow, and that pulls these particles along with them. Okay, so something has changed in the flow, and that manifests in the mass transport. Okay, so that is the reason. Of course, then the question is why, and then you have to go into the fluid mechanics of that stuff, right? But the signature in the transport is what is interesting also. Okay, so now, if there are no other questions, what I want to do is, before we go further into details, talk about the three big questions that we look at in this course. Okay. And these are big questions in the sense, not that they are big unsolved questions. Maybe one of them is, but big in the sense that I'm sure you would have had these questions in mind while you have done your existing earlier classwork, right? And these are the important ideas that we will be looking at and trying to answer during the course. Okay, so the first one starts with this Brownian motion, right, which we just saw the picture of. Okay. Okay, so again, I want you to think first about a single particle, right, and that it is just doing some kind of random walk. So I start with some particle here at the origin, and then I know it, because of this Brownian motion, it will spread out, right, in some way. And how can I describe the behavior of this particle? Right? So if I'm looking at just one individual guy. So if it's a random walk, I will do the math in 1D, right, but you can keep this picture in mind. So if it's a random walk, we say, okay, the particle takes a step, delta x, okay, and that this step it's taking in a random way, right? So I introduce zeta, and the zeta is some kind of a random number, right? Right, so I'll say it's a random number, and I say it has variance of 1. Okay, so you can do many things. The simplest case is you just say +1, -1, +1, -1, or you can take it from a uniform distribution between -1 to +1, or you can take it with a Gaussian distribution or whatever you want. Right, so it's not particularly important right now. So let's keep it vague. But the idea is this will contain some kind of normalized random number, which will tell me how I'm walking. Right, I go front, back, left, right. And then, of course, I can have an amplitude A. So I can have the same phenomena and take bigger steps. And then you can imagine, especially because of the situations we have been talking about, that if this random walk is coming out of something like that bacterial turbulence, then the distance I am walking depends on the time of observation also. So then I can put delta t there. Okay. This is just in a loose hand waving way, just to make the following point. Okay, so follow on for now. So I'm not saying precisely what this random number is, but I'm saying it's a random number with some bounded variance, right? So it doesn't have to be unity. Let's just say normalized. Okay, so it's some random number whose magnitude you somehow control by setting the variance, and then with this random number you can think of bigger, smaller steps depending on the time interval. Okay. But the point is that you would have to solve some such equation to track how this thing is behaving. Now you can easily imagine that I can do a computer simulation of this, right? I just do a random walk, I take forward step, backward step, keep tossing a coin to get this random number, and I can evolve this system. Now, because I have this delta t and delta x, right, I can imagine that relative to, let's say I'm observing this over some time 0 to capital T. If this delta x, if the delta t is relatively small, I can imagine that maybe I can write this like a differential equation. So I could say that, okay, this is some kind of discretization of something that looks like this. Okay, but this is a random number. Okay, so this brings in the idea that, okay, there is a differential equation, but with the right hand side that is random. And that is effectively coming, I mean, this random walk idea is some kind of discretization of this differential equation with some stochastic forcing. So again, right now I'm introducing all these things in an intuitive way, right? But the point is to show you that there are some difficulties in this. Okay, so let's set this aside as some initial thoughts. But I'm sure you can imagine doing this, right? So you can put one particle, do some simulation, take this random walk, you will get one realization. You repeat this to another particle, it of course won't do the same thing, right? Because these are random numbers, it will take some other path. And you can do this again and again, but the point is if you do enough of them, the population will start to spread. That's like what you saw in that, in those pictures that I showed you. So if I were to plot the probability versus x, right, this is the x-axis. And this p is the probability of finding a particle at a certain place at a certain time, right? So this is the probability distribution, right? And if I start with some distribution like this, so I put all the particles here, and then I wait for some time, right? After some time, it will do something like this. I'm trying to draw a Gaussian curve, but okay. So this is at t prime, this is at t, and t is greater than t prime. Okay, so I start at some localized thing, and then because they are moving around randomly, of course, all our intuition tells us that it will slowly spread. And in fact, if you do this, it will in fact spread. Okay, you can do this simulation, it will spread. This is what we mean by diffusive Brownian motion. So this is the individual perspective. But now we also know, okay, that I can treat this same problem as imagining I put a drop of dye or drop of ink inside a bath and I watch it. That what's going to happen? It's going to spread diffusively. right? Because that ink is made out of ink molecules, right? And those individual molecules are doing this thing, so that the concentration itself will spread. So if I can, instead of thinking of the individual perspective, right, I can directly go to the collective. Right, if I think of all those dye molecules together, then I can obviously define a concentration field. And this concentration field will diffuse. So I can start with a drop of dye here, the concentration is high, and then as it spreads, the concentration will decrease, eventually it will become some low uniform concentration. Right? So how would I describe that if there is a field C? What equation will I use to find how the concentration field will evolve? Yeah, so the diffusion equation, can you tell me the equation? So if I'm looking at evolution in time, right, like this, so I'll say dc dt. Right, so this is the diffusion coefficient. Okay, so this is the standard unsteady diffusion equation. Okay, and this will of course give me some nice behavior, like if I start something here, I'll get it will spread out. Right? So if this is the initial thing, and then this will be lighter, and then this will be very light, and you get that. So it's just going to spread out. In fact, it will look exactly like this if I do a 1D cut, right? And I plot the concentration, right, I'll get the same thing. And in fact, these things are same modulo some assumptions of, like, say, infinite dilution and no interaction between the different individual guys, right? The population is the concentration. Because then I want you to think about, right, this could be an ensemble of each time I put one particle, only one, do an experiment and then do the statistical ensemble, I'll get this. But I can also think of it all happening together, provided it's sufficiently dilute, right? Then I will get this. So you can see the connection. Okay, so now I'm sure you have come across this in your courses already. And the family of questions coming from the first point, right, is one sec. So you have this connection between the individual and the collective, and the question is, how are these things related? Specifically, how is the SDE, right, related to the PDE? And the important thing is, here there is no randomness, right? It's a fully deterministic partial differential equation. But it's coming from somehow from the random SDEs. Right? So how do you go from this stochastic setting to this deterministic setting? Right? Obviously, this has to do with going from individual to collective. Right? But how exactly does that happen? Right? And then at the end of this, the practical sort of question is, how is the connection between the amplitude of the random walk A, right, how big the steps I take are, right, with the, now what will the A be related to here? Right, obviously D, right, that's uniparameter. So these things are obviously related, the question is how. And this is only in the setting of simple Brownian diffusion. But we will ask these questions in this simple, well understood setting, but you can raise the same questions in much more complicated scenarios. So for example, instead of this being just an inert particle in a bath, it can be an inert particle in a turbulent flow. And I can again do this thing, except that instead of having A here, I'll say dx dt equal to V, the velocity of the fluid. But that velocity is coming from a turbulent flow, right? It's a turbulent flow. So that V will be fluctuating in time for all, it will look to us to be random. So instead of having this, which is coming from Brownian, where zeta is a true random number, I can have dx dt equal to the turbulent flow velocity V. And then that will give rise to some kind of spreading, because we know that things diffuse, effectively look like they diffuse. So I can write some concentration field here like this. Right? but now I will have advection. We'll come back to this point. But again, what I was saying is the same connection you can make in more complicated settings, either because it's being advected by turbulence, or maybe the particle, go back to the bath setting, no flow, but the particle can be complicated. So instead of having an inert particle, I can have a bacteria or something that is swimming. Right? So along with Brownian motion, it also has its own intrinsic motion. Right? Biological systems have this kind of behavior. They're called active Brownian particles. So in those cases, you can ask the same question, right? So I can always do this simulation. Instead of, along with the Brownian noise, I can add some other forces acting on this particle. I can put a particle and put a magnetic field or put an electric field and give it some drift and do what I like. So I can always make this equation of motion more complicated. Can I then derive an equivalent concentration field equation? Right? That's a nice question. If I can do that, then it's in some sense much easier to solve this. Right, and depending on the setting. But this is just one-time solution. Here I have to do a large number of simulations and so on. Yes, and sometimes it's easier to get, I mean, this I could in principle maybe even solve analytically. Right? I can't do that here and so on. Anyway, so this is the first set of questions, okay, which has obvious practical relevance, but I think also intellectually it's important to understand it, because you have seen both these things separately in your coursework, but not how they connect. Not in more broadly speaking, how the microscopic connects to the macroscopic. Any questions? Yeah, somebody had a question.
Sir, in that liquid in which you have suspended, put the droplets, like basically inserting in the bulk of the liquid in the middle, just one drop, not dropping it, because otherwise.
Right, sure. Yeah. But I mean, so there are different ways to realize this, but even if you forget now about the liquid and so on, just think of it as a thought experiment. Right? Even then you have the same situation. Right, so even if you forget about liquid and so on, just think of this thing. I have a point that is doing a random walk, and it will give you this behavior. Right? And I can obviously write this equation for that. And the question is, how do I get this from that? Or if I start with this, can you write that version of it? Right? So even in this ideal setting where there are no other complications, this is still an important question. Okay. And it's something that was dealt with very recently. So the other nice feature of this course and stochastic calculus, etc., is all the developments happened in the 1900s, so last century. Right, so this connection, in fact, was developed by Langevin and Einstein. Okay, before that, we didn't know how to deal with this. In Brownian motion also is relatively new. So in terms of the long history of science, all these ideas are actually quite recent, and the mathematics of them even more so. Right? Because as we will see, I will take you through Langevin's treatment of this problem and Einstein's. Okay, and then both of them they get to the same answer, which is correct, but there are questionable things because they're kind of feeling their way through. And it's only much later that mathematicians formalized these things. Right? So some of the ideas we will be doing in this course were developed only in the 1950s and so on. Right? So it's very recent. Okay, any other questions about this? So I hope the first point makes sense, right? Okay, so let's move on to the second question. Okay, so the second point is mathematical, motivated by we saw on top. So let's forget about the constant A for now and just say that I have something like this. It looks like a simple differential equation, right, for the evolution of some quantity x, except that this right hand side zeta is now a random variable, okay, which at every time it's like tossing a coin, right? You're getting a random number which is unrelated to anything that came before. Okay, so this is random. And if you like, it's a white noise in time. That means each time I take a value for it, it will be completely unrelated to what came before. It is like tossing a coin, uncorrelated. Fine, so this is the kind of equation that we will have to deal with, right, as we saw before, right, for example, from a random walk. And what I want to point out here is that if you treat the equation in this naive fashion, as if it was a usual differential equation, it will not make sense and you will find yourself in all kinds of trouble. And to motivate that, let us first consider a usual ordinary differential equation to see why things make sense there and what is the problem with treating this in the same way. Okay. So let us consider a usual ODE. So this is like some kind of, I'll put it in quotes because it's not the mathematical correct way to define an SD. It's just the intuitive thing that we would think of doing, and we're going to see why that is problematic. So hence the quotes. But first, let's consider a usual ODE, okay, which formally looks the same. But now this f of t is some smooth function. That means its derivatives exists and it's differentiable. So this is now some smooth it doesn't have to be different. It could be Lipschitz continuous, but for now, let's just say f prime is there, it exists, is bounded. Okay. So this is the kind of usual ODE we are comfortable with. You put it in MATLAB, you can use ODE 45 happily, and you'll get a solution. Okay. So why does this make sense? Because now here, if we have this, we can think of writing the formal solution like this. Right? So if I want to know the time evolution of x up to some time capital T, right? Right, so the evolution of x starting from time 0 will be the time integral of this right hand side, right? The same thing formally I could do there. Right, so here too I could say this, right? Okay, so you can see that whether this makes sense really depends on whether this integral makes sense the way it does here. So now let us consider this integral and remember why this works. Okay, so this is the usual integral, specifically a Riemann integral. Okay, and the way we would, so how do we know such an integral exists that it makes sense? Is we would construct the partial sums. Right? So in other words, if you look at the definition of this integral, we would say that such an integral 0 to t, right, I can approximate it using the partial sum. So what I do, I take f and I break it up into pieces, right, and sum them up. So you imagine I have some function like this. This is f, right, it's doing something nice, and I can make pieces of it. Okay. And like, let's say there are n pieces. Then I would do a summation. And let's assume that these intervals delta t are the same size for simplicity. Okay. So now this would be defined as some approximation to this, we hope. And then as n is taken to infinity, you should converge to something unique. Only then you can define that unique thing as the integral, right? If it doesn't converge or if the answer is somehow not unique, then you're in trouble. Okay, so how do we know that? So basically, if I take n to infinity, the delta t of course is related to n, right? So I have fi capital T by n. So the intuition is as n goes to infinity, I'm summing up an infinite things, but each of which become infinitely small, right? And the idea is these things should somehow balance and give you a finite answer. So how do I know that this whole thing, if n goes to infinity, will be finite? Any thoughts? If you remember your basic calculus. So obviously it's summing up some stuff. If this was 1, correct? If fi is 1, suppose, right? Then you're just summing t by n times, so the answer will be t. Okay? So that just means if this is constant, I can immediately make the argument. So just replace this with its maximum value or some bound. Right? So what it tells me is any bounded function f, you can define the integral. It's obvious, I don't have to do the algebra. Right? So if I replace this with some upper bound, which is larger than f everywhere, I can take that value outside and say whatever this is going to be less than upper bound into capital T. So it definitely is going to be bounded. It won't blow off to infinity. The only so it will convert somewhere. Only question now is whether is about this fi, right, which you didn't ask me yet. So what is this fi? Right? So in each interval I have different values of f, and I can in principle choose f anywhere. Right? So that means this is not unique, right? So here I am saying fi is the first point. Okay, and then this is fi plus 1 and blah. Okay, so I'm just defining it this way. So this is the definition if I choose fi to be at the beginning of the interval, but there is no reason to do this. So what we need to show is that if I choose fi anywhere else, I will get the same answer. Only if that works, the integral can be defined. Right? Otherwise, I will have infinite answers depending on where I choose the f. Then it's not a well-defined mathematical quantity. Do you remember why this works? Or what should I do to prove this? So if I take the alternative and I say, let me say s and tilde, okay, is a different choice. I can say f at I plus alpha delta t. So I take, I mean, the notation is not great, but the idea is, okay, let me call it ti. That's better. So this is ti, this is ti plus 1. Okay. So instead of evaluating f at I means f at ti, the start of the interval, I do it at some fraction alpha way along the interval. Okay. This is also perfectly fine. But I need to show that this is going to be the same as this, as n goes to infinity, of course. Any idea what I should do? Remember I said f is, I'm going to assume is differentiable. Will that help you? Can I write f somewhere here, a distance alpha here in terms of fi? What should I do?
Basically, go along the slope.
Mathematically, what should I do? That's why I should do a Taylor series, correct? So using a Taylor series, I will have, right, fi plus alpha delta t into the derivative, right? But delta t is just t by n, right? Into now f prime at ti. F prime is a derivative, okay? This whole thing into t by n. We agree, so that's just Taylor series, which I can do if the function is differentiable. That means f prime is bounded. So now you see, as I take n tending to infinity, what's going to happen? This guy, the n that comes from here, I can use the same bounded argument, will cancel off. I'll get some definite result here, right, which will become n independent. But here I'll have a 1 by n left over because it's like n square. So this will go to 0. So as n goes to infinity, the difference, the error that comes from choosing f, or the difference between the various choices I can make for where to sample f, that difference vanishes as n goes to infinity. Okay? This is why the Riemann integral works out. So in other words, the existence of this integral and its meaning has to do with the fact that the f is changing slowly. Slowly in the sense that it is smooth. Right? So the value at some time just ahead of my current time is going to be different by an amount that is proportional to how much the time difference is. That is the meaning of it being, right, continuous. Lipschitz continuous, differentiable. Right? I don't have big jumps. But now you think about this, right? The random white in time. It is the precise opposite of this thing. And therefore, if I were to do this, I cannot, if instead of f, if I put zeta, right, I cannot do this because of course it's not differentiable, right? If you look at a random signal, I mean, it is the opposite of that, right? It's not differentiable anywhere. It's not continuous also. Sorry, it is continuous, but nowhere differentiable. It's continuous in the sense that it doesn't, so okay, I should be careful. It depends on the x will be continuous, right, but not differentiable. This is discontinuous also, it's just jumping. Okay. So what is important now is that in the case of that integral, right, so zeta, if you like, ti plus alpha delta t, right, is completely unrelated to zeta at Ti. Right, which means if zeta corresponds to a random number with some variance, the difference between these two on average will be the variance. Right, so it will jump completely. And then there will be no 1 by n coming. So this difference goes like 1 by n in a smooth function. Here this difference will be some constant independent of n. And therefore, when you take the limit, this n will get knocked off by this. And the answer you get will have a finite difference that depends on where I chose to sample the function. Okay. So this integral it depends on where zeta is sampled precisely because the zeta at every time instant is uncorrelated to the previous time. So what this means is this thing is basically not defined in the usual way. Right? Or another way of saying this, if you are a mathematician, is fine. I cannot say that all, but I can always define my choice. A physicist would be totally alarmed by this, right? Mathematician would say, fine, let me just define my integral where zeta is evaluated at the first point of the interval and get on with it. So then I can get a finite, well-defined quantity. Okay, but the corollary of that is, of course, that you have infinite possible integrals now because you can choose any point. Okay, so this is the first beautifully complex thing about stochastic calculus is that you have different possible interpretations of a stochastic integral. So when you write such an integral, and this is random, there is no one way to define the integral. You can get different answers depending on how you choose to define it. Okay, and there are two particular choices that we are going to discuss that are mostly used, okay, for reasons that will become clear during the course. Right. So there is the Ito definition. Okay, and this is based on this problem. It will use zeta at Ti. Okay, this is called the Ito integral after the Japanese mathematician Ito. And then there is the Stratonovich. Okay, and this uses the midpoint. Okay, so zeta evaluated at the first point of the interval after you discretize time. Right? So if you choose always this first point, then you get an integral which is called the Ito integral. If you choose the midpoint, you get Stratonovich. And you choose these two for specific reasons. We will see that later in the course. Okay? But this is just to point out now that why stochastic calculus is different. Right? Because the integrals are not defined uniquely. They depend on where you choose to sample the noise, right, when you discretize SDE. And depending on where you sample the noise, you will get different answers. All right? And that itself, I think, is quite interesting. Okay, so it overturns many of our usual assumptions, right, about things. Any questions? Of course, I'm sure you have questions, right, but related to what I just said, we will unravel this strange onion as we go along. Any questions about the things I did here? Okay, so again, all of this is meant to be a kind of intuitive first look, okay, at what the issues are. We will do everything more precisely as we go along. Okay, so this is question 2, okay, which was how to deal with these SDs, right? So question 1 is you have SDs arising out of individual particle descriptions, how to relate it to collective PDEs. Question 2 is what to do with those SDs, right? And that is obviously going to be important because when we try to go from the SDE to the PDE, we first need to understand what this SDE is. So that is where question 2 arises. Okay, and now very quickly, the last 5 minutes, let me talk about question 3, which is in fact the hardest, most profound question, but it's easy to state. So question 3 is something like, can we model turbulent mixing, right, by a random velocity field. Okay. So what I mean is, again, imagine that plume stack or the bacterial turbulence mixing problem. Right? So I want to study the transport of some kind of particle or some kind of dye, and let's say I do it in terms of a concentration field, and because it is mixing because of a turbulent flow, the equation will be this, right? I'm going to neglect diffusion. So let's say I'm looking at a collection of particles which are non-diffusive, okay, or the diffusion is super small. So then any mixing I see of the concentration field is coming from this advection term. All right? And so now again I'm coming to the same question that so let's say I put a dye and I let the flow evolve, right? How is this dye going to mix? So any particular realization, it will do some meandering thing, right? But what if I look at the ensemble average? So because this situation of putting a dye cannot become stationary, it will keep spreading. I can repeat the experiment many times and look at what happens on the average, right? So you would expect it to mix, right? If I put a dye, maybe in one particular realization the dye doesn't move for some reason, or it stays there. But if you do this experiment many times, you would expect that on the average it should mix, right? That is what turbulence does. Or you think of the plume stack scenario, that you inject the dye here, as you go forward in space, all kinds of funny things happen. But if you watch the movie for a long time, it will seem like it is spreading, right? So there should be advective spreading. Okay. Now how to see that is you take the ensemble average, right? So let's apply an ensemble average over many experiments. So I just take the average of this. Right, the time derivative will come out of the average. So the rate of change of now the average concentration, right? How does the average spread over many different experiments? Right, I have to apply the average to this guy, 0. Right, so everything now depends on this. Okay. So now this is where things are interesting. The V is unrelated to the concentration field, right? It's a random velocity field. So I've thrown away the Navier-Stokes. I'm saying, can I model the mixing by some random field suitably chosen? So because V is random, it has nothing to do with this, right? These are two uncorrelated things. The C will also move randomly because of the velocity, right? But at any instant of time, the velocity I get has nothing to do with the concentration. I'm just generating it randomly. The concentration will, of course, depend on the velocity of the past, but at the same instant of time, they are not correlated. Right? So then I can split this. No? I can write this as, right, because the average of two uncorrelated variables are the product of the averages. No? That's a definition of having no correlation. Right? So because V and delta C at the same time are uncorrelated, it seems like I can do this. But when you do this, what is the mean of V? So if you think of some isotropic turbulent situation where there is no mean velocity, right, this will go to 0. And this is what will happen in you put a beaker and you put a stirrer, right? Of course, it will go around, but that will not mix. The mixing is happening because of the isotropic random fluctuations, but that doesn't have any mean velocity, right? So the mean being 0 will knock this off, and it will tell you that on average there will be no mixing, okay, which is absurd. Because we know from our experience, you put it in a turbulent flow, it will mix, it will spread. There should be some, in fact, some diffuser-like thing should happen. So what this exercise shows you is that naively, if you proceed, you get something absurd. So something is obviously wrong and going from here to here. Or our assumption of replacing the velocity with a random field would lead to there being no mixing. Therefore, this modeling has to be done in a careful way. That when one replaces turbulence by randomness, if you just do it directly, you will get something like this, which is obviously wrong. So this shows you that even though it looks like something random is happening, there is a nuance in that. So I'll leave it here just to point out again that this is why this question is interesting, right? And our course will help us understand why this actually does not go to 0. But in fact, if we do things properly, right? So at the end of CL677, you will see that this actually gives you something like turbulent diffusivity okay, so instead of being 0, it will actually give you that, but there are several steps that we have to modify to understand how it gives you something like eddy diffusion. Okay, so that is the third question that we will address, and this of course is not a full answer. It's a highly restrictive setting. So the general problem of turbulent mixing remains open, but we'll learn many ways of thinking about the problem. Okay, so let's stop here. Thank you for your attention.